अपनी कार में या
I am starting the meeting.
पब्लिक ट्रांसपोर्ट यूज न करते हैं को जाने की व्यवस्था करना ये जरूरी है और हम ये व्यवस्था करने के बारे में जरूर सूचना देंगे।
बरोबर किती जण आले सगळे इले
गुड मॉर्निंग
काय झालं काय
Good morning, everybody. Can you hear me?
Good morning, sir.
Hello.
Yes, sir. I can hear. आवाज जाते
Hello. Can you hear me?
Sorry, but Amy said don't. Yes. Yes.
Who said this? Yes.
Connecting to audio. Oh, your photo बघा. डन करायचं कुणाचं दाखव तोंड दिसते यावर
Hello.
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 Yes. Good morning.
Hello. Good morning,
Good
sir.
morning, sir.
Good morning, sir.
So I can see Shivanjali,
Good morning, sir.
Rahul.
Yes, sir.
Who else
Yes,
can
sir.
hear me? Just give your name. Who can
Rahul
hear
morning,
me?
sir.
Rahul. Yes.
Sir, Shivanjali.
Yes, sir.
Shivanjali. Yes.
Hello, sir.
Ruturaj.
Pooja.
Pooja. Who Pooja? Yes, Pooja. Okay, so shall we start?
Yes, sir.
Yeah. So today we will cover our 6th unit part, which is the PID controllers. In our previous lectures, we have already covered some of it, but for those who were not present or just to make this lecture complete, we will cover it in quick succession, and then we'll solve one problem, which will be very important from the exam point of view. Okay. Yeah. So now you can see on your screen the slides, right? Can you see
Yes,
this
sir.
PID controller slide?
Yes.
Yes.
Okay. So as you can take out from the name PID controller, PID stands for proportional, integral, and derivative. And when we talk about controllers, if you remember well, in the very beginning of our course, we have talked about the basic diagram of the PID controller, right? Or any controller, in fact. Like controller is
Yes,
placed
sir.
like here in the loop before the plant, right? And the plant output is measured and given back to the input side and compared with the reference value. And the difference between the reference value and the measured value is the error. So for any controller, as you can recall, for any controller, the error acts as an input. So similarly, for the PID controller, the error is the input, and the output of the PID controller is given to the plant. And then the plant will adjust itself, or the values of the plants, or the controlled variable will be kept within the required range. This is how the basic controller works. On a similar note, PID controller will be placed before the plant, and it will try to keep the value of the controlled variable within the specified limits. Okay. So this is the block diagram of the PID controller. As you can see, there are 3 separate components. The first one is the proportional one, the actual one, which has only a gain, component, and the output of this section is proportional to the error signal. The second component of the controller is the integral component, where the output of this controller here is proportional to the integral of the error, right? E of t is the error, integral of error multiplied by ki. This ki is the proportional gain. Okay. So the output of this block is proportional to the integration of the error. And similarly, the output of the derivative controller is proportional to the derivative of the error, right? Output of the derivative controller is kd multiplied by d by dt of e of t, means the derivative of the error. Okay. And when we say it is a PID controller, all these 3 components get combined or get summed up in this summing junction, and that's how we get the CPID. Here also at the bottom you can see the output of the controller CPID of t is equal to Kp into Et, which is the proportional component, plus Ki into E of t dt, which is proportional to the integration of the error, plus Kd det of t, which is output is proportional to the derivative of the error. Okay. So this is how the PID controller works, right? Now,
Yes, sir.
to convert this equation into Laplace form, we can see if we take Laplace transform of the this equation and take E of t here, so we get the transfer function of the controller, and that is equal to Kp plus Ki into 1 by I plus Kd into S, right? This is just the Laplace transform, and E of S goes down here, right? So this also can be written as Kp into 1 plus 1 upon TIS plus TDS, and this TIS in this case is Kp upon Ki and TD is equal to Kd upon Kp. Now these two terms, this Ti is called the integral time and TD is called the derivative time, right? And in this case, Kp is called the proportional constant, Ki is the integral constant,
Integral
and TD is
constant.
the derivative constant,
Derivative constant.
right? Okay.
Yes,
So
sir.
this is what we have already seen. Now, some of these things we will just skip ahead, because what we want actually to talk about is how the PID parameters are found out, and that is done in the PID tuning, right? The process of selecting the controller parameters Kp, Ti, and Td to meet the given performance specification is known as the controller tuning. And a couple of methods have been proposed by Zeigler and Nichol, which suggests some rules for tuning of this PID controller, and that is done experimentally. That is not done analytically. That analytically means by hand or by calculations, but it is not done that way. It has to be done experimentally. So even if the mathematical model of the plant is not known, we can use this. We can use these methods, and of course, if it is known, we can always use these methods, right? These will not give us final values. These will give us a good educational guess for Kp, Ti, and Td. And now we will see how these two methods are designed. There are two methods. First method is open loop method, and second method is the closed loop method. In the first method, what we do, if the plant does not involve integrators or dominant complex conjugate poles, then the system response will be like this S curve, right? If the system does not involve integrators or complex conjugate poles, what it means is the system is either critically damped or overdamped. Then the system response will be like this. And in that case, what we do, we first find out the step response of the system, and then we put a tangent like this to the step response, and we find out these two values L and T. L is what? Where this tangent line intersects the x-axis. Value from 0 to that intersection is L, and from there onwards to the final value of intersection point is T. This L and T, these two values, we use and find out the Kp, Ti, Td based on what controller we are using. Right? So for only proportional controller, Kp will be T by L, and Ti will be infinity, Td will be 0. What it means is that Ti and Td component, if you go back to the equation, we can see here, Ti becomes infinity means this term becomes 0, Td becomes 0 means this term becomes 0. So only remains is Kp. Right? So it becomes only a proportional controller. Similarly, if it is a PI controller, Kp and Ti will be like this, and for a PID controller, these will be the values of Kp, Ti, and Td to start with the controller. Right? This is the first method, but when it can be used, when there are no integrators in the plant and there are no dominant complex conjugate poles in the plant, right? These two conditions are required to use the first method. If both these things are not possible, then we have to use the second method. But in the second method, what we do, we convert the PID controller into a pure proportional controller. Okay, means what we do, we set Ti equal to infinity and TD equal to 0. Okay,
0.
means only proportional component remains, only KP remains. So the diagram becomes like this. Only KP is there. It is a proportional controller. We give it to the plant. So what we do, we start increasing KP from 0 and we gradually start increasing the value of the KP. At some point, there will be a situation where the plant will start exhibiting sustained oscillations. Now, what it means, sustained oscillations? Sinusoidal oscillations. Means the system becomes marginally stable, right? This thing we have seen twice. Once at the time of root locus and also at the time of Raut-Hurwitz criterion, right? We have seen ACR, which is the critical value of the gain, which makes the system marginally stable. Right? Okay, so what we do, we increase KP so that the system becomes marginally stable and exhibits sustained oscillations. Okay, now whatever the value of KP is, we use this as one important parameter, KCR. Okay, now from KCR and the sustained oscillations we have got. So for those sustained oscillations, there will be a period of oscillations like this period of oscillations. These two values we capture, and based on these two values, we find out the values of KP, TI, and TD. So in case of P, obviously TI, TD will be like this. TI will be infinity, TD will be 0. Only KP will remain, and for KP, for proportional control, KP will be 0.5 KCR, right? The KCR is the critical gain, right? For PI controller, the values change. The KP will be 0.45 KCR and TI will be PCR by 1.2. For PID controller, again, the value will change. KP will be 0.6 KCR, TI will be 0.5 PCR, and TD will be 0.125 PCR. Now, again, remember, what is this PCR? This PCR is the period of sustained oscillations that we have obtained, and KCR is the critical gain that we have obtained, right? Critical gain, which has made the system oscillatory, right? Now, this is the actual method which we have to do experimentally, right? So, suppose you have a plant and you want to find out the PID tuning parameters. So, this is how we will do. We will make the integral and derivative component 0 and start increasing the gain only, which is the remaining part. We will start increasing the gain from 0, and there will be one point when the output will exhibit the sustained oscillations. We will stop there. We will note down that gain to be KCR, and we'll also note down the period of sustained oscillation. Now, this is what we have talked about, the practical aspects of the PID tuning, what we will do in real practice. Now, coming back to our subject, or from the exam point of view, what kind of problems we will face, right? If somebody asks you a problem, they cannot give you a problem in your problem, right? So what we will get some kind of a problem like this. There will be a system given to us. This is the equation of the plant, and this is the controller that we will have to tune. This is the PID controller. The question will be something like this: to apply Zeigler-Nichol's tuning method for determination of the values of KP, TI, and TD. Right? So, what is this system? Plant, third order system plant. We will add a controller to it, and there is a unity feedback in the system, right? So this kind of a problem now we will try to solve. Now, just a question: which method can you use? First method or second method? In this case, which method can you use for this plant? See, for the first method, what was the condition? First method, the condition was there should not be any integrator. But here we have an integrator. This S, right?
Yes.
S in the denominator, 1 by S component is there.
Yes.
So here we cannot use the integrator, right? Sorry, here is an integrator, so we cannot use the first method. So we will have to use second method. This is first thing, right? Now, second method says you will increase the gain and you will find out KCR and then find PCR and then we'll find out KPTITD. So how can you do this? So we have to use another way of obtaining the KCR. See, we have the plant, right? And what we do in the second method, instead in the PID, we use only KP, right? So what it will become? The equation will be like this: KP and the plant and this. So if you see what is the closed loop transfer of this system now, transfer function, it will be like this. KP is these two blocks are in series. So KP upon S into S plus 1 into S plus 5. And since it is a unity feedback loop, the closed loop transfer function using our closed loop formula. What is that formula? GS upon 1 plus GS. Right? Using that formula, we get the closed loop transfer function as this. Right? Now, using Routh-Hurwitz stability criterion, what we can find out? We can use this as the characteristic equation, the denominator polynomial, right? We use the denominator polynomial as characteristic equation of the system, right? And then what we will do? This is the, see here, this is the denominator polynomial. This we will use as characteristic equation and then what?
Find out the value of K.
Exactly. Then we will use Routh-Hurwitz criteria like this. See, this is the characteristic equation from the above equation. Here you can expand this S into S square plus 6S plus 5 multiplied by S. So S square plus 6S S cube plus 6S square plus 5S plus KP. Now this is the characteristic equation. We apply Routh-Hurwitz criteria on this. So we find out our Routh array. Okay. So this is the Routh array now. 1, 6, 5, KP.
5
right?
KP.
1, 6, 5 KP. Here we will get 30 minus KP, right? 6 into 5, 30 minus KP upon 6.
By 6.
And here we will get only KP, right?
KP.
Correct? Now, for stability, what is the condition? All these first column elements should be positive.
Positive or negative.
So this, yeah, positive, all positive or all negative, right? Now
All
these two are
negative.
positive, means this has to be positive. Okay, so for stability, this has to be positive, and for marginal stability, this has to be 0.
0.
Right? Because when this
Yes.
becomes 0, this row becomes 0, and it
0.
means the system will be marginally stable.
Marginally stable.
Correct? So we make this 0 and find out value of KP. So 30 minus KP upon 6 is equal to 0. So 30 minus KP is equal to 0. So KP is equal to 30.
T.
Right? From this equal to 0, if we make this equation, equal to 0,
0.
what we get? KP is equal to 30.
KP is equals to 30.
Correct? So KP equal to 30 will make this S raised to 1 row as 0, and that will make the system marginally stable.
Marginally stable.
Correct? So the gain which makes the system marginally stable is called the critical gain, and that's why this KCR is equal to 30. So we got one of our value. What we wanted? We want KCR and PCR, right? We want these two values, right? So we got the first one. We have got the first one, right? Now the second one. What we want? What we want is the PCR.
PCR.
PCR is the period of the oscillation. So for that, what we will need? We will need frequency of sustained oscillation. Means what? Frequency of sustained oscillation means what?
Omega n.
Omega n, right? So for that, what we will do? We have this characteristic equation. and we will substitute s equal to j omega in this characteristic equation. Okay. And kp we will substitute as 30. kp we substitute as 30, and then we will find out what is the value of omega for this. Okay. Now, if I do this, j omega raised to 3, 6 j omega raised to 2, 5 j omega plus 30 equal to 0. Now, what we get here, j omega raised to 3 is, can somebody tell me? J omega raised to 3. No? Minus j omega cube. How? J into j into j.
Minus
J square is minus 1, right? J square is minus 1
into j
into j. So minus j
into j minus
into omega cube. So here, that term is right here. J omega into omega minus omega square minus j omega cube. Okay. Here I have actually skipped one step. Go further. Okay, you can simplify this in your own way also. It doesn't matter. You can simplify this in your own way also. Okay. J minus j omega cube plus 6 into j omega square. J omega square is what?
minus omega.
Minus
minus
omega square.
omega.
Minus omega square, right?
Omega square.
Yes, minus omega square.
Minus omega square. J square is minus 1. Omega square is omega square. So minus
Omega square.
omega square into 6. So 6 minus into minus omega square. That is minus 6 omega square will be here. Plus 5 j omega plus 30. Okay. Now what we have done is just rearranging the terms. This 5 into 6 I have taken from here. 5 into 6. Okay. 6 from here. So from the second and the last term I have taken out 6 common. Okay. The second term and last term I have taken out 6 common. Right? You can check yourself. From here, if I take out 6, what remains is minus omega square. And from here, 30, if I take out 6, remains 5. So 5 minus omega square into this 6 common. And for the first and the third term, we have taken out j omega. This j omega into bracket 5. And this what we said, minus j omega cube. Right? Minus j omega cube for this. So multiplication of these two minus j omega cube. Okay. Right? Now what we get here? 5j omega square is equal to 0. Okay. Omega is equal to square root of 5 radian per second. Now what is this? Omega is equal to square root of 5 radian per second. This is what? This is the value of omega when the gain is KCR. When the gain is critical gain. Right? So at the time of critical gain, what we get? Value of sustained the frequency of sustained oscillations that we have got now. Okay. What we have got? Omega radian per second. Okay. So if omega is somebody has done a lot of these things, you should clear annotation. Okay. Omega is equal to square root of 5 radian per second. Now what actually we wanted was PCR, which is the period of sustained oscillation. So that will be equal to 2 pi by omega. Right? We want PCR in seconds. So 2 pi by omega, right? How we are getting this? Omega is equal to 2 pi f, right? Omega is equal to 2 pi f, frequency in hertz when we say about, right? So f is equal to 1 by t. That's why t is equal to 2 pi by omega. So we have got omega 2 pi. So we'll get this value as PCR. So now from the table that we have already seen, Kp is equal to 0.6 kcr, right? Kp is equal to 0.6 kcr, Ti is equal to 0.5 pcr, and Td is equal to 0.125 pcr. This table you have to remember all the time. Okay, which table I am referring to? I am referring to
Number 2.
this table, right? I am
Closed
referring
loop
to this
table.
table,
Okay.
PID. Okay, Kp, Ti, and Td you are getting.
TD.
Kp, Ti, and Td we are getting here,
TD.
right?
TD.
This table you have to remember all the time. Okay, so we have got KCR which was equal to 30 and PCR which is equal to PCR is equal to 2.8099. So using these two values, we will find out the three values of Kp, Ti, and Td. Okay, so ideally the problem, if it is expected to find out the Kp, Ti, Td only, then we can end the problem here. But if it is asked to find out the transfer function, then just additional step that you will have to do in the transfer function equation,
Put the value.
you are just to substitute those values and you get your answer. Okay, so this is what the GC is. GC means what? Transfer function of the controller only, right? This is not the transfer function of the full closed loop system. This is the transfer function of controller only.
Yeah.
So what will be the
Controller
final
only.
diagram if you want to see? The actual diagram is like this. This is what we have found out, GC, right?
Yes.
In this case, we have found out GC. So if it is asked to draw the full diagram of the control system, then just write that equation in this block and it will be complete. It is normally it is not asked. Generally, what is asked is to find out the values of Kp, Ti, and Td. Okay. In some cases, you may be asked to find out Kp, Ki, and Kd. What I'm saying? What is the difference? Kp, Ki, and Kd. Here we have done Kp, Ti, Td.
T and TD.
So what you will have to do in that case? You will have to remember this equation. Ti is equal to Kp upon Ki and Td is equal to Kd upon Kp. Okay. So from these
TD upon KP.
relationships, you will have to find out the values of Kp and Ki. Okay. Are you getting what is the difference? We have found out Kp, Ti, Td. And in case if you want Ki, then Ki will be equal to what? Kp upon Ti.
KP upon TI.
Right? Kd will be what? Td into Kp.
TD
Right?
into KP.
So this way you can also find out the Kp, Ki, and Kd. Okay. So this kind of problem normally is asked for 8 marks generally in your exam. So it is very simple to remember, and the only important thing what we have done is to find out the value of Kp using the Raut-Hurwitz criterion. And before doing this, before applying the Raut-Hurwitz criteria, we must find out the characteristic equation. Okay, so here is the big step. You write down Kp here. So Kp multiplies here, and you have to first find out closed loop transfer function of the plant of the system, right? And on the closed loop transfer function only you will apply the Raut-Hurwitz criteria. So this is one of the most important step which you should not miss or make any mistake, because once you do this, you get Kp by equating this to 0, this kind of term to 0, and then you find out your KCR and omega n. For finding out omega n, if you don't want to do this, you can do another step also. Can somebody say which one?
Auxiliary equation.
Exactly. You can find out auxiliary polynomial from here, right? 6s square plus Kp.
30.
6s square plus 30. Right? You will anyway get the same value, right? 6s square plus 30. So s square is equal to minus 5. Right? So you are going to get the same thing. Omega n is equal to square root of 5.
Yes.
This is what we have done in the at the time of root locus,
Router.
right?
All right. Yeah.
From route array, we have done the for the root locus where the point of intersection is with the imaginary axis is. For that, we have done the same thing, right? So that also we can do. We can find out the omega n. And omega n, remember, omega n is in radians per second. And what we want only in terms of PCR is in terms of seconds. Right? Omega is equal to 2 pi f. That basic equation, omega is what? Omega is the frequency in radian per second, and f is what? Frequency in hertz.
Yes.
Frequency in hertz.
Right? So omega is equal to 2 pi f. That equation you should remember. From that, using that equation only, we are getting this. Right? PCR is period of oscillation. So f is what? 1 upon PCR. Right? F is 1 upon PCR. Am I right?
1 upon PCR. Yes.
1 upon
Right.
f.
Is equal to P.
Right? 1 upon f is equal to PCR.
Yes.
This is period. This is frequency. Right?
Yes.
When we are talking about this frequency is in hertz. This is
Hertz.
seconds.
Okay.
Right? So
Yes.
anyway, all these things will add up. What we have? We have omega is equal to 2 pi
F.
f. Right? Omega is equal to 2 pi f. So we are using this same equation to find out f, and f is equal to 1 upon PCR. So this is how we get PCR is equal to 2 pi by f or 2 pi by omega. Okay.
Yes.
So any doubts regarding this point?
No.
No, sir.
Yes, it is clear to everyone.
Yes, sir.
Yes, sir.
Yes, sir.
And is there a problem regarding the first step or first method?
First method. Okay. Now you can see first method again is this method you are talking about, right? Yes. Hello.
Yes.
Yeah. Ask. Yeah, you may ask the problem. What is the problem? Yes.
Sir, if there is a problem, can we take a problem which is on the first method?
Actually, we cannot solve any problem on the first method. The problem is, if you can see the first method, what it does, we have to get a output of the step response in the first method, right?
Yes.
I mean, you are saying if there is a problem in the exam, right? That's what you are talking about. Yeah. It is not possible to get a problem on this kind of on this first method, because what is happening here in the first method, we have to apply step input and get the step response and then find a tangent. This we cannot do on paper. Are you getting the point?
Yes.
Because this is applicable when the mathematical model is not known, right? That time we will do this kind of method. This method I have covered just for the sake of completeness. And at all there is something, what you will be given will be a curve and L and T will be given to you. And from that, you will have to just make these calculations. But this kind of problem is not possible on paper.
Okay.
Okay?
Yes.
Okay, sir.
These tables you must remember, right? These tables, basically the second method important table, this you must remember completely. Okay.
Yes, sir.
Somebody is talking, but I cannot hear.
त्यासाठी तो आणखी 4 दिवस लागतील.
Yeah. Yeah. So shall we stop here?
Yes, sir.
Yes, sir.
Yeah.
Yes, sir.
Okay, sir.
This PPT I have already shared on our WhatsApp group.
Okay, sir. Yes.
Okay, sir.
This is a PDF I have already shared with all of you on the WhatsApp group, so you can refer this again. And if you get any problem, you can always contact me on our WhatsApp group. Okay.
Okay, sir. Okay, sir.
Okay, sir.
So
Thank you so much.
you are
Thank
always
you,
Thank you,
welcome.
sir.
Okay.
Yes, sir.
So thank you
Thank you,
for
sir.
listening and keep studying. Okay.
Yes, sir.
Sir.
If you can come
Yes,
across
sir.
any problem, you can contact me. Okay.
Okay, sir. Thank
Okay,
you.
yes.
Okay.
Thank you
Yes,
so
sir.
much.
Thank you, sir.
So okay. Bye.
Bye bye. Thank you,
Sir.
sir.
Yeah.
Bye.
Okay. Bye.